Plop, plop, fizz, fizz. Oh, what a relief it is.
Alright, this video is over states of matter and how those matters can change within each other. So you see this chart in your note. You have your three states of matter written up top: solid, liquid, and gas. Those are the three states of matter that we're actually going to talk about today. You're going to be responsible for this chart and how each one of these states of matter is different from the other. So we're going to go through the solids first. The thing about solids is it has very, very close molecules. So the example I'm going to use for this is a brick. Obviously, bricks are solid. Now that brick has a definite shape. You can't take that brick and form it into a circle, or you can't make it flat. The shape of the brick is going to hold true, and that brick has definite volume. You're not going to be able to push on that brick or pull on that brick to make it have a higher volume. Now, because the molecules of the solid are very close together, it's going to have very restricted motion. It does have vibration and a little bit of rotation, but those molecules really stay in one spot. It's like standing in a really compact line. You can turn around and talk to the person behind you. You can turn to your left and talk to somebody on the other line, but you can't really get out of line. You're going to have to stay in that one same spot. Now, solids have a very high density. That should make sense. If you put solids in water, most of the time they will sink. Solids, on the other hand, are not very compressible. Like I said, with that brick and its shape and its volume, you can't push on that brick and make it any smaller. It's not going to happen. Those molecules are too close together. They're going to compact against each other, and it's not going to be compressed hardly at all. And molecules don't expand much with increases in temperature change. They do expand a little bit, but not enough to really be considered. And then diffusion, if you remember, diffusion is going from a high concentration of whatever you're working with to a lower concentration of whatever you're working with. So if you stack up a whole bunch of bricks on one side, they're not going to diffuse until you have two equal stacks of other bricks. It sounds ridiculous, but that's the way they work. They diffuse so slow that you can't notice it. Now, liquids, on the other hand, they have molecules that are close, but not very close. They're still within contact with each other, but they're not quite free to move around at will, but they still have more ability to move around. Liquids can take the shape of their container, and they have a definite volume. So you take a cup of water, that cup of water has conformed to its container, and if you take that cup of water, say it has 5 milliliters of water, and you pour it into a gallon container, you're still only going to have 5 milliliters of water, even though you poured it into a bigger container. The only thing that's going to change is the shape of the water itself, the shape of those molecules. The molecules are close. They do have some freedom of motion. Now, if we take a look back at that line, that crowded room, now you can kind of jump over to that next line. You can go over and say hey to your buddy on your next line. You can come back over. You can move to the front a little bit. You can move back a few spaces, but you're still not quite free enough to move around at will. The density of liquids, they're called medium-high densities. There's less than solids except for water. Water's kind of the keynote. But generally, liquids sit on top of solids. Then liquids are somewhat compressible. You can take that 5 milliliters of water and compress it really, really hard and might be able to get down to 4.5 milliliters of water. You can take a look at your water gun. You pump that water gun up real high, and all of a sudden you have a little bit less water inside of your tank. Liquids do expand slightly with increase in temperature. It's enough to take notice of it. And the thing with liquids, they diffuse easily, but less rapidly than gases. For instance, if I pour out a whole gallon of water on one side of the classroom, eventually it will spread out and cover the entire classroom. It will have a nice even layer across it throughout the whole classroom. Whereas the diffusion of the bricks, one pile of bricks stay in the same spot, where if I pour a big old jug of water in one spot of the room, it's going to spread out through the whole room. Now, gases are very different from liquids and solids. Molecules of gases are far apart. They take the shape of their container, and the key thing with gases is that they also take the volume of your container. So you can take a gallon full of gas and then pour that gallon full of gas inside of your classroom or inside of your bedroom. And now the volume of that gas, that gallon of gas, is now the volume of your classroom. Now, gases are free to move in all directions. They have a high degree of fluidity. They can go wherever they want. They can cut to the front of that line. They can go over to another line and cut in front of that person if they want. They don't care. They're going to go wherever they want to go. Now, gases tend to have low density. Obviously, gases are going to sit above liquids. If you think about a swamp, they've got that mist sitting above the water. And then gases also easily can be compressed into smaller volumes. You can take that gallon of gas and you can release that gallon of gas into your bedroom. Gases are highly expansive with increases in temperature, assuming the volume of the container can change. Great. And gases, because they're moving so quickly and they're far apart, They diffuse easily. So make sure you understand the differences between solid, liquids, and gas. Take note of the key changes that we talked about. Okay, so do the example problem in your notes. Go ahead and pause this, see what you can figure out based on the chart we just filled out. Here are your phase changes that you're going to need to know. You need to know the main 6. We don't really talk a whole lot about plasma, but I'm going to leave it up there just in case you get into it in your class. But the 6 main ones are these 3 different subsets. If we take a look at the bottom, these arrows indicate which direction you're going. And you're going to want to be able to draw those arrows and know which direction it's going to, what phase it begins with, what phase it ends with, and what that phase change is called. So let's start with our water. Let's start with liquid water. And let's say we're going to freeze that water. If we freeze that water, it's going to go from a liquid to a solid. So our water froze, become ice. Now our ice, we're going to leave it out in the heat, and our ice is going to melt. So we went from a solid to a liquid. Now if we start with our water, and we boil our water into a gas, that's going to be called vaporization. Then if we take that gas and we turn it into a liquid, think of liquid, and we take that gas and turn it into a liquid. Think about the dew that forms on your windows at night or on the grass in the morning. It's going to be condensation, taking the gas or the water out of the air and then turning it into liquid water. Now, 2 that might not be very familiar to you is going from a solid to a gas. And a good example of that is going to be dry ice. If you think of that dry ice, it's a solid to start with, but if you look at it, it's going directly from a solid to a liquid. We call that sublimation. And then we can go the opposite direction. It's kind of rare, but going from a gas directly to a solid, that's going to be deposition. So in addition to knowing all 6 phase changes, you need to be able to classify them as endothermic and exothermic. So here's a definition of endothermic phase changes. Anything that's labeled as endothermic is going to take in heat, or heat enters the system. And a good way to remember that is EN, EN. Endo enters into the system. And then you have your 3 phase changes right there. Fill that in your notes. Those are your 3 phase changes that are classified as endothermic. Exothermic, on the other hand, if endothermic, it takes in heat. Exothermic releases heat. You can take that EX right there, and EX. Exothermic exits, endothermic enters. So exothermic, heat's releasing from the system, and so here are your 3 phase changes that are being considered exothermic. And each one of these, on the exothermic, the substance is becoming cold. So freezing, deposition, condensation, that's all kind of going down in your phase change diagram. Endothermic, you can kind of see everything is kind of getting hot. It's going up. Phase change diagram over here. So take a look at these. By the time you come to class, I want you to be able to tell me why each one of these phase changes is considered endothermic or exothermic. It just takes a little bit of thought, and you'll figure it out.
Flop, flop, fizz, fizz. Oh, what a relief it is.
We have only to remove those who oppose us.